Okay, yeah, so we talked about quantum gates on 1 qubit. Remember that everything has to be unitary. And we noticed that not doing anything on the other qubits is expressed by using a tensor product with a identity operator, 2 times 2 identity matrix. Not the Cartesian product, the tensor product. That's important. Also talk about this phase change gate, which changes the phase, the angle on a complex unit circle for the second case when the qubit is 1, but not when the qubit is 0. And thus we can rephrase the Pauli Z gate as a phase gate with an angle of 180 degrees pi. We also discussed the Hadamard gates. First, the Hadamard gate on 1 qubit. Here's the matrix representation. Here's the truth table, linear, so it suffices to say what it does on the basis vectors 0 and 1. It's unitary, operates on 1 qubit here. So on the other qubits, we need to spell out the identity tensor product with the identity operators. Now with our first quantum circuit, right? Combining these to a full width quantum circuit operating on all the input qubits. And then we can add another quantum gate to further process it. So let's say the input state, all qubits are in the 0 state. And remember, this is, we abbreviate this in this way. So that's a binary 0, 6-digit binary 0, right? This way, or this is the same. Now what happens after this state? So we prepare the qubits in the trap in this with this state, let's say, and then we have them evolve through the first quantum gate, n-bit quantum gate. What will be the result? Well, the other qubits will be unchanged. It's the identity after all. But the first qubit will be given by this column, linear combination of 0 and 1. And the others are still 0. And now, well, this is like hello world in quantum programming. Well, anyway, what's next in hello world? Output, right? In quantum circuit, output means measurement. So let's put a measurement device here and recall, what does it mean to do a measurement in quantum mechanics? Measurement in quantum mechanics is intrinsically random, probabilistic, non-deterministic. But the axiom says, what are the probabilities? What are the possible outcomes? Well, the first qubit is in state 0 with, I'm going to say 50% probability, and in state 1 with 50% probability. Now, when I say 50% probability, that's of course a lie, because that's classical thinking. Here we have quantum mechanics, and what does the axiom say? The probability is the inner product absolute value squared. So what's the inner product of this vector with 0 absolute value squared? We'll take the inner product with this. Inner product of 0 with 0 is a unit vector, right? Divided by square root of 2 squared. That's 50% indeed. And similarly, Other possible outcome is 1. Calculate the inner product of this vector with the 1 vector. Take the absolute value, which is 1 over square root of 2, square it, which is 1 over 2. So indeed, classical result after the measurement will be 0 with 50% or 1 with 50%. And after the measurement, the state will have changed. It will be either 0 or 1, like looking into the box with Schrödinger's cat. Before we make the measurement, it's this superposition of 0 and 1. Schrödinger's cat is superposition of dead and alive. After making the measurement, the state will have collapsed to either one of the two with 50-50% chance, and then it will be in the state 0 or in the state 1. So usually when we design quantum circuits, we make the measurement only at the very end. Because from that on, that provides the result, and then everything is kind of destroyed. All the entangled states that we've created here with this additional Hadamard gate are destroyed. Also observe that there's something sequential and something parallel in this circuit. It's a nice succession, nice follow-up to our chapter on parallel computing, on parallel circuits. Here we have quantum circuits. We already talked about quantum gates on 2 qubits, so I'm going to skip that. And we did talk about Hadamard gates on 2 and more qubits. So Hadamard gate on 2 qubits. These are the possible values for a 2-qubit system. This is the matrix of the 2-qubit Hadamard gate, unitary, 2-qubit. And this is where parallelism happens, right? So here, these two Hadamard gates operate concurrently. And if we have Hadamard gates not on 2, but on 3, 4, 6, or n qubits, right, before we proceed to n qubits, observe the output. So if we start this with the same initial state, 0, 0, 0, 6 zeros, right, like in the previous slide, what will be the state after this 2-qubit Hadamard gate? Well, it will be the first column, right? 0, 0 is the first basis vector. First column is the result after this operation. And this is here, right? Will again be a superposition, but now of 4 possible qubit values. 0, 0 up to 1, 1. That's entanglement. N scaled by 2 to make it a unit vector. Right, and I was starting to talk about what is the concurrency here. If we have not 2 but n Hadamard gates operating all n qubits, then they do that simultaneously. So that's concurrent. And if we start with the 0 states as in the previous slide, then after this n-fold Hadamard, starting with 0 gates, this n-fold Hadamard will contain all possible qubit values. Right, so here it's 4 possible values of the 2-qubit system. And this means 2 to the n possible values of an n-qubit system. Right? N-bit counter can have 2 to the n many values. An n-qubit system is described by 2 to the n basis vectors. And this is an abbreviation for 0, 0, 0, 0, 0, 0, 0, 0, 1, 0, 0, 1, 0, and so on, counted in binary up to 1, 1, 1, 1, 1, and 1s. And each one with the same weight, So each one would be equally likely if we were to perform a measurement after that. And the weight is given by this because that makes this vector a unit vector. So this is a kind of concurrency similar to the Boolean gates that we discussed in chapter 9. And the largest concurrency, the largest number of gates that would flip simultaneously in a Boolean circuit on n inputs would be n gates, right? One gate taking care of each input. Usually we had this tree. That means n over 2 gates switch simultaneously. Take the maximum of pairs, add 2 pairs or whatever. That's n-fold parallelism, small n. N, the number of input bits in a parallel circuit. And here, that's n, small n-fold concurrency operating n Hadamard gates on n qubits. Yes, you have a question. So you're asking about n, the number of qubits?
Yes.
Right. That's exactly where I'm heading. Thank you. Thank you for paving the path to my next comment. So the message I want you to take here is this is a similar kind of parallelism as we discussed in chapter 9. It's n-fold parallelism, where n is the number of input qubits. But that's not quantum parallelism. Remember, accelerating something by a factor of n, that's certainly good, right? But here we're trying to accelerate something exponentially, right? We want to factor integers. That's what Shor does. And the best known classical algorithm for factoring integers take exponential time, exponential in the length of the input, that is exponential in the number of bits or qubits. And Shor does that in time polynomial in the number of qubits. So exponential acceleration. So we need a different kind of parallelism. So I call this one concurrent. That's kind of like the classical one, but now with quantum gates. We also have some sequential part, like with classical circuits. First round in a tree, then the next round, next layer, same here. Only here it's drawn from left to right. Is the time procedure. But what is quantum parallelism? To illustrate that, recall the case of maybe 4 qubits. I can still spell out all possible values of 4 qubits. Of course, that's how many? That's 16, right? So here are all possible values of qubits. Some are hidden with these dots. And after these Hadamard gates, remember all occur with same weight, 2 to the n over 2, when n is equal to 4. That's simply divided by 4. And you verify that this is a unit vector. Each one occurring with same probability. So if we now were to perform a measurement after this n-fold, 4-fold Hadamard gate, each one would occur with same probability, with probability 1 over 16, right? Classical probability. But where's the quantum parallelism? Quantum parallelism happens if we now add sequentially another gate. Of course, must again be unitary. Your homework is to check that the multiplication, composition of 2 unitary matrices is again unitary. And now if we apply this state to a unitary. And since U is linear, unitary, so this is sequential in this direction. So we apply U here to the state, and since U is linear, it means we can move it into the bracket and apply it to each term individually. That's what you see here. And so now U operates on all 16 possible qubit values simultaneously. And that's quantum parallelism. Not 4 bits simultaneously, but 16 possible values of the qubits simultaneously. Or more generally, not n qubits, but 2 to the n possible values of these qubits simultaneously. So here we can also move the U inside. So this was concurrent, but only small n-fold. And operating on all these states simultaneously, that's quantum parallelism. Capital n-fold, 2 to the small n-fold, that's exponential acceleration. This is maybe a little bit compared to suppose you have a classical Boolean circuit with n input bits. And suppose you could run that on all possible n-bit input values. So 2 to the n possible choices for the input, and suppose you could run your classical circuit on all of them simultaneously. That's what quantum parallelism does. So on the one hand, huge acceleration. On the other hand, huge restriction, only linear unitary operators. What can we do with that? Yeah, that's still a huge open question. Is there an actual quantum supremacy beyond Shor and Grover and so on? We won't answer that here, but we're heading for Shor's algorithm. We also already discussed the Fourier transform, first reminding you of the discrete Fourier transform, which you may or may not have learned about in CS204, discrete mathematics. And its quantum counterpart, operating on input vectors of length dimension 2 to the n, or n qubit. So again, there's some concurrency in this direction. There's some sequential evolution happening in this direction. And by definition, yeah, I think I've asked you to verify that the discrete Fourier transform is indeed unitary. But this is an exponential size unitary matrix because our state space is of exponential size. So when I give you n times n unitary matrix and ask you to turn that into a quantum circuit, that might result in an exponential size quantum circuit, right? But the goal is to have polynomial size quantum circuits. Polynomial sequential time, but also polynomial size, right? And it turns out for the quantum Fourier transform, this is possible to express this exponential size matrix using only a polynomial number of tensor operations and matrix multiplications. So superficially, this is an exponentially large quantum circuit. The sum, defining it, has exponentially many terms, but, and this is where I'm skipping a little bit over the mathematical details, it can be expressed as a tensor product of only small n terms. Right? So the sum has capital N, that is exponentially many terms, expressed as, and that's mathematics, as small n-fold tensor product of these other operators. It is called tensor factorization. Most tensors do not factor, but this one is a nice one, and it does. Again, I'm going to skip a lot of mathematics here and show you the resulting circuit, turning this mathematical tensor factorization into such a circuit. You see, the circuit involves Hadamard gates, 1 qubit here, 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 and it involves controlled phase gates and 2 qubits, but which qubit is the controlling one and which one is affected the phase changes over time. This is sequential direction. And it has n rounds, and each round has n of these controlled phase gates. So the overall size of this circuit is, this is sequential. Overall size is quadratic. Depth is linear. And multiplication, first this, then this, then this. This is like matrix multiplication, right? First this matrix, then this, then this. Each one corresponding to a unitary matrix. So this composition of unitary or multiplication of unitary matrices turns into sequential progress through the quantum circuit. And tensor product, vertical, corresponds to concurrent, but not quantum parallelism yet. Quantum parallelism says we can always take this circuit and run it on all possible values or all possible configurations of the input qubit register simultaneously. And of course, the goal is to do it in such a way that it helps us accelerate computation. And now we've been talking already about quantum phase estimation, which is a kind of meta problem where the input is not just an input state, but also an input unitary matrix given by a quantum circuit on, let's say, m qubits. Now, we haven't really talked about how to input quantum circuits, and that's why I call this a meta problem, and I will return to that at the end when we talk about the particular U that is used in Shor's algorithm. So we fix such a unitary operator given by some m qubit quantum circuit. So it's a 2 to the m times 2 to the m matrix, and we're given an input state which is promised to be an eigenvector. And eigenvector means applying to this unitary matrix results in a scalar multiple of the input vector. And since the matrix is unitary, the scalar multiple, the eigenvalue, must be a complex number of magnitude 1. That's just mathematics. So magnitude 1 means it has form e to the 2 pi I theta, where theta is a real number between 0 and 1. And the quantum phase estimation problem asks you to output this theta. The eigenvalue, the exponent in the eigenvalue to the given promised eigenvector of U. Now, why is that an important problem? Some of you asked me at the end of last lecture. So I'm going to explain to you why this is important. First thing to observe is usually in courses like linear algebra or numerics. The difficult thing is calculating the eigenvector, or calculating the eigenvalue given nothing, only the matrix. Here, we give the matrix and we're given the promised eigenvector. So classically, how would you do that in course on linear algebra? Multiply the given eigenvector to the given matrix and just look at the first entry of the result and check if the first entry is the threefold of the first entry of the input vector. Then you know 3 is the eigenvalue, right? So you only need to look at the first entry in the resulting vector. Unless the input vector is 0 at this position, then you don't know it. Then you look at some other. But the thing is, multiplying the input vector to the first row of the matrix, input vector has exponential dimension. Matrix has exponential dimension here. So this naive standard algorithm that you would immediately come up with in problem in linear algebra works, but it will have exponential running time. And here we want to do better. So that's first answer to the question you asked at the end of last lecture. Why is this an interesting problem at all? And the second answer is because it's used in Shor's algorithm. So here's Shor's algorithm. Shor's algorithm is actually a hybrid algorithm. It combines classical discrete number theoretic algorithms on a sequential computer, and it makes subroutine call to a quantum algorithm, to a quantum circuit in the sense we have just seen before. So here's the algorithm. Specification: input is a composite natural number. And output is some non-trivial factor. Remember, the goal is to factor the integer x. Also remember that testing whether an integer is prime number or composite, this is well developed, right? Later, in chapter 5, after the midterm, we will discuss randomized algorithms, including one that tests whether a given integer is a prime number or not, very efficiently, very elegantly, in a randomized setting. Randomized. We will not discuss in this course the famous 2003 algorithm, AKS algorithm, doing that deterministically. So testing, that's one thing, that is settled. But if I promise you this is a composite number, if my test has shown this is a composite number, finding a non-trivial factor, factoring it, that's believed to be very hard. And it suffices to find one non-trivial factor, because if we have one, then we divide it by that factor, and then test whether the remainder is a prime number or not. If it is, then we're done. If it's not, then we invoke the same algorithm again to find another non-trivial factor. How many non-trivial factors can there be? Well, each non-trivial factor will be at least 2, right? That's the least non-trivial factor. So each time we find a non-trivial factor, then the magnitude of the number drops by at least 2, which means the bit length comes shorter by at least 1 bit. So if we have n-bit input, in the worst case, if all factors are 2, after n iterations, we will have arrived at the complete factorization. So finding one non-trivial factor is enough, and then we repeat it small n times, not capital N, but small n times. That's what Shor's algorithm does, and it makes some first hypothesis without loss of generality. Suppose the input integer is odd. Well, if it's even, we can quickly test whether it's even, and then we have non-trivial factor 2 right away. So that's not the interesting case. Also, suppose it's not a prime power. Why not a prime power? I think I leave that question for you. Maybe put it in the midterm. If it is a prime number, what are you going to do to find its factorization? And how long will it take using just classical number theoretic algorithms? For now, let's suppose that it is not a prime power. And it is not. Here's the algorithm. First step, pick a random number. Yeah, we'll discuss randomized algorithm in chapter 5, or we can use our quantum circuit with these Hadamard gates to create a random, equally distributed n-bit random number. Then calculate the greatest common divisor between this random number A and the input integer x. Euclidean algorithm, you know Euclidean algorithm, right? Euclidean algorithm uses this division with remainder, and it runs in polynomial time. And so that's not a problem here. Time polynomial in the bit length. Then check whether the GCD is 1 or not. If it's not, then that's a non-trivial factor, right? GCD means it is a divisor. It's even the greatest common divisor. So from now on, we know that the GCD is 1, which means that x and a are coprime. If x and a are coprime, then we know from number theory or discrete mathematics that multiplication modular x of a forms a group, finite group. So we can take a squared, a cubed, all modulo x. And doing that repeatedly at the end, we will arrive back at 1. And if we do it one more step, we're back at a, then a. So it's cyclic, right? That's number theory. And in this such cyclic group, classical mathematical concept is called the order. How often do we need to multiply a with itself to arrive back at 1? That's the order. Should be a formula explaining the order. It will come later. Yeah. Okay. So if this order is odd, then we're in bad luck and we go back to step A, pick another random number. That's bad luck because then we haven't found a non-trivial factor. And then there's some number theory and probability theory that says this won't happen too often. Also observe that step number 4 will use the quantum subroutine in a way that I'm going to explain on the next slide. So this is why it's a hybrid algorithm. So far, everything has been classical number theoretic algorithm. So if the order is even, then the order divided by 2 is an integer. We can raise a to that power, always modulo x, so that raising it to the power doesn't blow up, right? So all numbers will be between 1 and x, because we always take modular remainder with respect to x, plus 1, calculate the GCD, If the GCD is non-1, then we have again found a non-trivial divisor of X. Otherwise, again, we're in bad luck and have to start again with a different random number. And classical probability theory says this is very unlikely to happen, at least not repeatedly. Now, what again is the order? The order is the least exponent, the least number of times we have to multiply a to itself to arrive back at 1, modular x. And group theory says this number exists if and since a and x are coprime. You see how line number 3 is crucial, right? If they're not coprime, then we have found a non-trivial factor and we're done. If they're all coprime, then all this group theory and number theory applies. And then we invoke the quantum subroutine, which may or may not succeed. But if it doesn't succeed, we try again, and then number theory says we won't have to repeat more than a constant number of times, actually. So quantum phase estimation. Quantum subroutine to find the multiplicative order using quantum phase estimation. That's what this slide explains. How are these two concepts related? Our goal is to calculate the order of A modulo X, modular order. And we're going to use this the quantum circuit for phase estimation that I'm going to explain in the rest of this chapter. Most of it on Thursday. But here's the reason why we do want to do quantum phase estimation. So here's for you to remember. Want to calculate the order of A modulo X, which is this integer. Also, by the way, I use capital letters for numbers which can become exponentially large, 2 to the small n. And I use small letters for numbers that are polynomially related to small n. Right? Capital N is 2 to the small n. A, or let's say X, X is an n-bit number, actually it will be an m-bit number. Therefore, its value can be at most 2 to the small m. A can be as large as 2 to the m, small m. And K and R can be also as large as 2 to the small m. So X denotes the m-bit integer, which is to be factored or with non-trivial factor we want to find. And A is this random integer parameter, which is promised to be coprime, because if it's not, and we've already found the non-trivial factor using Euclidean GCD calculation. A strictly between 1 and x, otherwise it's not coprime, right? So what's the connection between this order calculation problem and phase estimation? To make that connection, I'm going to define a unitary operator. Remember, the input to the quantum phase estimation problem is a unitary operator, and here it comes. Unitary operator operates on a m qubit state, say the m qubit value encode in binary the integer L, capital L, and the resulting state should be L times A modulo X, that's an integer, m-bit integer, encode this in binary, so this is going to be another m qubit state. So this is how unitary operator linear is supposed to operate on the basis vectors. At least on those basis vectors corresponding to integers strictly less than x. Now, frankly, we're not really interested in what this operator does on input vectors that corresponded to binary L equal or larger x, but we need to define it because we need to make sure that this U is going to be unitary, right? Otherwise, we cannot realize it at all in this quantum circuit. So here's what we simply do in the other case. This is just mathematical definition. And remember what people have been trying since for 30 years, since Shor introduced this algorithm, trying to implement this operator, right? So far, this is just mathematics. And what does it mean to implement it? It means find the Hamiltonian corresponding to this unitary operator, and then implement an observable that realizes this Hamiltonian. But this is not our concern. This is a theory lecture, and we'll leave it to physicists and engineers to continue trying to implement that. Anyway, so I claim that this U, by definition, it's linear. We've only defined it on basis vectors, how it maps basis vectors to basis vectors. On 2 to the n-dimensional vector space, so capital M, that this is unitary. Check it yourself. This is where it's so important that A and X are co-prime to each other. Remember, if it's unitary, then we know that its eigenvalues are of this form with a phase parameter theta, real phase between 0 and 1. And the goal of this slide is to explain to you how this phase parameter that we want to determine in the quantum phase estimation problem relates to the order that Shor algorithm wants to know as a subroutine. And here it is. So if we raise this operator, unitary operator U to the kth, and the result is the unit matrix, that's the same as if we raise the integer A, remember the random number A, to the k, and the result is 1 modulo x. And this is the least such k, that's the order. And from the previous line, we know that this means that theta must be an integer multiple of 1 over r the order. And you see how this starts connecting dots. So if we could determine theta, then mathematics tells us theta is an integer multiple of r. So by finding numerator and denominator of this fraction theta, then the denominator will give us the order. And we can do that. Here's the explicit formula for an eigenvector. Check that this is an eigenvector to this eigenvalue. And also, if we add up all these eigenvectors and scale them all with the same weight, 1 over square root of r, then verify that the result is this basis vectors. Not the one with all zeros, but the one with all zeros and 1 at the last digit. So for now, believe it, but at some point, I want to encourage you to verify that at some point. Because that's the connection between quantum phase estimation and the order calculation which Shor's algorithm, hybrid algorithm, needs to factor. So if you got confused or lost, also time is almost over for now. for the rest of this chapter 11, I'm going to show you how to solve the quantum phase estimation problem. And why? The answer is contained, although not quite obviously, but in these two slides, the slide how modular order relates to phase, and how order determine the modular order allows us to factor the integer in Shor's hybrid algorithm, which is classical and uses quantum subroutine to calculate the order using phase estimation. So, what again is phase estimation? We're given this unitary operator matrix. Just saw it on the previous slide. Here it is. We're given a promised eigenvector, one of these guys. We've calculated this. These are the eigenvectors. These are the eigenvalues. Then quantum phase estimation will give us this one. And then from that we extract R. Okay. Now what does it say? Approximate. Because, yeah, we need to fix a certain, in general for phase estimation, theta will be a real number, any real number between 0 and 1. So we need to do the estimation approximately, but with sufficient accuracy so that we can recover which fraction is being approximated, right? So it turns out that n-bit approximation to the quantum phase theta will be sufficient to recover numerator and denominator. And denominator is what we're interested in. Now in the last minute, you might have spotted the gap in this whole endeavor, because remember, the promise to quantum phase estimation is that we're given an eigenvector. How can we prepare this eigenvector? If we can prepare this eigenvector, then most likely we're going to need to know R anyway. And this is where the last equation, summing up all the eigenvectors, comes into account. We can certainly prepare this initial state, right? So if we apply our future quantum circuit for quantum phase estimation to this vector, since it's going to be linear, it means applying to this sum, which means applying to every single of these eigenvectors, which we don't even need to know. We just need to know that they're there. Prepare this, apply our solution quantum circuit, and the result will be, what will be the result? A superposition of these eigenvalues. All of them. Like Schrödinger's cat, but not just in 2, but in 2 to the m possible states. And then we perform a measurement, and the state will collapse to one of these. We don't know which one. They're all going to be equally likely. But whatever state it collapses to, the resulting value will be of this form. The numerator, we cannot predict, but the denominator is what we're interested in. And this is where the quantum parallelism happens. So Thursday, I'm going to explain how to solve the quantum phase estimation problem, but keep in mind what Shor actually does. It applies the quantum phase estimation circuit to this vector, which means it applies it to all these eigenvectors without having to prepare any of these eigenvectors. We only prepare this one. And then perform a measurement which will result in collapsing to some such fraction. We don't know which numerator it will collapse to. We don't know which eigenvector it will collapse to. But the denominator is what we're interested in anyway. So that's all I wanted to say today. On Thursday, I'm going to conclude this chapter by explaining how to devise a quantum circuit for the quantum phase estimation problem. Now you know why it's important, how it's related to modular order, how it is invoked as a subroutine in Shor's algorithm. And at the end of Thursday's lecture, I'm going to give you some advice on the midterm exam. Thank you.